Hi guys, I am Minh, and welcome to the reinforcement learning session up here at Adobe. Let's see. So I don't know if all of you have seen this demo yet, but if you have and you know what's going on, then please come up here and explain it to me. But okay, so we're here to talk about reinforcement learning, and the general concept of it is actually really, really easy to understand. But what's going on here? Obviously, there's a Pac-Man sitting in the middle. He's traveling around, and you can see these rays. And those rays represent actually sensors, but that's the Pac-Man's line of vision, so to speak. So every time it sees a wall, you'll see it in magenta, and it's marked that way. And every time it sees a ghost, it's marked in the white line, like that one right there. And the cherry is, let's see, go very fast. There we go. The cherry is actually green. So over time, basically, we're using a very, very, very simple algorithm for this. It's called DQ network. So what's generally happening is that there's a Pac-Man sitting on a universe or an environment, right? That ticks every second to animate everything that you see on the screen. But generally speaking, all that's going on is the agent, which is the Pac-Man, gets to move left, right, up, or down. Those are just 4 discrete actions, okay? So we call that this action space. And beside that, there's also a state space, which is pretty much represented by the sphere of influence. It's basically what it can see. So the state right here is it can see ghosts, it can see walls, and it can see cherries. That's basically it. That's all that they can see. The other thing that's novel about it is that every time it actually touches a ghost, there's a negative reward to basically penalize bad behavior, right? And every time it touches a cherry, it's actually a +1 reward. So it's a good thing. You're encouraging it to do it again the next time it sees the same or similar type of state. Does that kind of make sense? That goes okay so far? Okay, good. But just keep this in mind because those are really the 3 things that are in play when we're dealing with this framework. So just think of everything as state inputs, right? Inputs is those sensors. Positive or negative reward, which is +1, -1 for neutral, 0. And that's an action, and an action. The action is up, down, left, right in this case. So that's it. And if you want to see what happens when I click make stupid, basically it just unlearns everything. So there's something called a brain or a neural network that's actually in play in the background. But that brain, when you click that button, it just resets it to nothing, and now it has to learn everything from experience again. So it has to go around and touch random things, and then start to tweak its ebbs and flows to behave more optimally for value. Value just being positive reward. Okay? So that's the general synopsis. What are we going to do? We're basically going to peruse, which is what we just did. We'll overview what DQN is, what reinforcement learning is, and then we'll go through more practical examples. And in this case, basically we'll deal with, I guess more like an app or restaurant or recommendations for like Yelp reviews, those kinds of things. So or even like dynamic UIs. So how do you get it to the point where maybe a brain can suggest a UI that's more specific to you, for instance. So it's personalization on a scale of 1, basically, like personalization of 1. So if I go there and I'm tagged as, male, 36 years old, into karaoke, likes drinking, all these stuff, and all that goes in as an input, theoretically, the brain can look at those inputs and suggest an appropriate action. And in this case, it might be like a UI. So that's what we'll be talking about today. Okay? So the weird demo, you already saw it. Why do we need to keep looking at these kinds of things? Mainly because technology keeps changing. So as a technologist, we should really be aware of what's going on around us. Maybe it's useful to you in your day job, maybe it's not, or maybe you'll find a creative way to just enjoy programming. That's okay too. And my success scenario today is if you find this presentation entertaining and applicable, so much so that you start to play with the code, then that's a win for me. So that's basically it. Okay, so what is reinforcement learning? Officially, it's a subfield of AI, and it's a framework of learning to solve decision-making problems. And how does it do this? Just through trial and error with occasional rewards. Think of it as teaching a baby how to walk or teaching a dog how to sit by giving it treats, for instance. And Deep Q Network, why did I pick this one? Honestly, it was the easiest one to reason about, easiest one to implement, and this is just one algorithm of reinforcement learning. But with Deep Q Networks, it's basically just reinforcement learning using neural networks to estimate something called the Q value. And what is Q value? Generally speaking, it's just the performance of each state action pair. Does that make sense? So if I see this environment as it is right now, and I do this action, what is the perceived reward I'll get out of doing it? So it's just keeping track of that. And that determines what it will do, okay? So if you've studied machine learning at all, it's very similar to supervised learning, which is teach by example. And by that I mean, okay, I have a bunch of files, right? I have basically a Word file, a PDF file, I have a, MP3. And I want to start classifying it. I'm like, oh, if I see an MP3 file, I want to put it into the MP3 folder, okay? And if I see a PDF file, let's put that into the PDF folder. And I'll train the machine learning agent through my own exercise, like my own saying what is good, what is bad. Does that make sense? So that's supervised learning, regular classical machine learning, teach by example. Except in reinforcement learning, in this specific example, the good or bad is automated or rather computed by just the reward system. So the reward system is enough to come up with some inherited policy to suggest an action. So reinforcement learning is just teach by experience, kind of like these cats right now. They just learn over time that if I touch that bell, I get a treat, so why not touch it? And here we are. We're going to talk about Deep Q networks, which is right in the middle right there. So it's just one implementation of many, 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 many different ones. But I picked this one because it's model-free, mainly, meaning that you don't have to do much math. And basically, it's just rewards and penalties make sense to me. Really easy to think about. Easy to talk about, I think anyone can pick it up. And what does this framework look like? So again, we have just an agent. An agent is just a thing, a robot. And the agent executes an action. So the action is something that you can define. It does something, right? And then it observes the new state of the environment, and it also potentially receives a reward. So you can kind of see in that diagram over there, that's the feedback loop that's just on repeat pretty much forever. So there's a forward function that prescribes you an action. Let's turn right on the street, okay? And you go do that, and maybe it leads to a crash. Then it's like, oh man, okay, next time, maybe not turn right on Allen Street, okay? But it's just a feedback loop over time, and it takes hundreds, thousands of iterations, generally speaking, before it converges to some good policy, where it's doing better than random, right? Better than random is what we're really going for. Okay, and the agent's whole purpose of life is to maximize the current reward, right? Plus the discounted future reward. And what the heck does that mean? It's kind of like stock prices. Like Adobe's stock price is not just how much money Adobe has in the bank, right? It's a representation of that, plus also discounted future earnings that Adobe will earn, Does that make sense? So that's why it's important. Why do we need that? Because we don't want to learn like this for that, right? Because the thing is, what if your tastes change and the action that you thought was good already, was good is no longer good? Like, how do you plan for that? So that's why there has to be a discounted reward. There's a lot more to it. But generally speaking, from this number, this Q value, we'll adjust the policy so that you compare what you predicted you would get to what you actually got. And then you can lower or raise the Q values that way. And just to recap, action space, think of it as outputs. Okay? Action space, we need to know these three things. Action space, we generally want it to be discrete, meaning that it's limited so that we can reason about it and it's not like a gazillion, And think of it as what the agent can do in the environment. And second thing is state space, really important. It's the inputs that go into this black box. And it can be fully observable or partially observable, which makes sense. It's like chess. Chess, if you look at the table or the board, you'll know exactly what state it's in, right? It's totally exposed. And then the Pac-Man example, really all I can see is that circle. That's your influence, basically. So that's limited. And you can think of the state space as what can the agent see from the environment. And reward, that's the obvious one. It's what does the agent get from doing the action, given my inputs. And what that starts to look like is this table on the lower left right here. It's kind of like a state machine, right? For every state S1, if I see the environment looking like S1, probably I should do A2 as the action, right? And then I go ahead and I hit A2, and I'm like, okay, let's do action 2. Let's turn right on Elm Street. And it leads to a really bad reward. Even though I expected it was a +2, I got a -10 or something. Then I'll use that experience to lower that number. So that's just dynamically changing up and down, basically all the time. So that kind of makes sense, right? But now the problem is when the state space and the action space gets really, really, really big, computing these values verbatim or computing them actually gets really slow. So that's a problem. And that's why people brought in basically a neural net to represent this Q table. And what that just looks like is, okay, right at the beginning, the neural net will just set everything to like 0, right? And then it'll go do something, it'll have an action, it's like, oh shoot, I got a +2. Then it'll just slowly start to like back propagate, and we'll estimate those same Q values at the end as like A0, A1 right here. So that's about as far as we'll go with this. But how does it compute these estimates then? So there's a mechanic called the loss function, and that's what I basically just said. It just computes how off we were from our initial prediction, and then it'll tweak. It'll tweak it up if we were wrong in a good way, and it'll tweak it down if we were wrong in a horrible, horrific way. So that's pretty much all you need to know about backpropagation and how the network kind of like fixes itself. And you can kind of see it as just raises, ebbs and flows across like a landscape or a field. So yeah. So just a little bit more terminology before we go into examples and then basically some code. But terminology, the environment, like you said, can be fully observable like chess or partially like poker, right? I can only see my hand and I make decisions based on what I see as my hand and what I've seen play, but not necessarily what you're holding. Environment can also be deterministic or stochastic. Deterministic is, oh, if we're playing a game and the inputs are 2 or 2 and the game is to add, then it's always going to be 4. There's no randomness, no nothing to it. It's always going to do that. And just the state that I have right now is enough for me to predict with 100% accuracy what my reward would be. Or it can be stochastic, meaning like stock market response to news, right? There's chaos to it. There's like some randomness. Even though I think that like I should always do this, there's still the off chance where the environment screws me up. And it doesn't happen. For instance, the stock market, right? If you get good news, you expect the price to go up. But sometimes we see the good news wasn't good enough, apparently, and it went down. Okay? It's kind of like that. And the environment can be static or dynamic. And this kind of makes sense. It's like checkers, you make the move and it's pretty much sitting there forever. Or dynamic, like flying a drone, because the wind can go in and like kind of like, you have to kind of learn on the fly. And actions can be discrete, recommended. Discrete, like Flappy Birds, you have one button, you press it and it just hops. Or it can be continuous, like driving a car. You tweak a little bit to the left and it's, oh no, that's not enough. And tweak a little bit more to the left. So that's pretty much as far as we need to go here. But now examples. So we're just going to start thinking about goals, states, actions, and rewards. So I have like 3 examples here. So the first example is pretty simple. It's a cart pole. So it's a cart, and you can imagine a pole like pretty much standing upright on it, and then gravity acts on it as you move, right? So the purpose of the game here, the goal, is to balance the pole, like keep the pole always balanced and on top of a moving cart. And the state here, what do we have to see from the environment is the pole angle, the angle in which the pole is right now, right? The angular speed, how fast it's dropping. And then you also have the cart position, where we are, and the current left-right velocity. So we have those things as inputs. So the possible actions here is just let's move left or right, right? And the reward in this case is, let's just say it's +1 reward, 1 apple, for each second in which the pole is upright, okay? So you'll just see over only about 300 iterations, it starts to do what's going on the right side. It's able to learn that, like, oh man, when it's twirling like that on the left, it doesn't really give me much joy, you know? So here, the next frame, when the reward structure is well defined, performance should converge to optimal policy over time. So that right there is actually a true like tracking of the cart pole example. So after about 150 tries or so, it will keep it upright all the time, basically. And it sucks at first due to randomness because it doesn't know the environment that it's in yet. Okay? The second one is actually even cooler, and this is the reason why I started like kind of studying it a little bit. In about 2013 or 2015, news came out that reinforcement learning was used to play Atari games, right? And the coolest thing about it is, okay, let's just look at Breakout, the game. The whole point of the game is to basically break the bricks and don't die. Don't let the ball like pass you, basically. But the coolest thing about it is, okay, the goal is obviously to break as many bricks as you can without dying, right? But the state here is the interesting one because it's a composite. Like if you look at one frame, the bottom left frame, you won't know what's going on at all, right? You don't know if it's the ball's going up, down, left, right, to what angle, who knows? So what some people decided to do was, okay, let's just represent that state as a composite of 4 frames. And from it, you can determine, oh, all velocity is going this way. This way. Makes sense, right? So that's the novelty of that. And the actions, again, is just left or right, and the reward is something similar to 1 point for every brick you break, and -1,000,000 for dying, for instance. And over time, it actually does know how to play it, better than humans, unfortunately. But yeah, other examples, which is more real life, I guess, would be customer embedding. So Google does this quite a lot, and a lot of other places now. But it's for app suggestions, ad suggestions, food suggestions. And the goal is to provide quality suggestions, right? Things that will enact me, or make me enact, or go buy, or go to the brick and mortar store, whatever. But the state here is the customer tagging. So what that is just any info, personal info that you can grab on a person before they hit your site, for instance. Purchaser graphics, what did I buy in the last 7 days? Or demographics, like I am a male from Boston, you know? And whatever I like or dislike, what my temperament is. Or, for instance, purchase graphics, if that's even a word. Google told me that, so maybe it's right. But even if that's, basically if I went and bought like a Barbie, all of a sudden, like, you know, you start seeing like, okay, basically Barbie ads everywhere. It's pretty much the same type of thinking here. The action here is just to prescribe one or many possible suggestions. And the reward could be +1 for every click view, +1 for if I actually went and bought it, or if I visited, I don't know, the toy store. So reward structure obviously has a huge impact on strategy. So here's some more like minor, small examples, but just things to be mindful of, because if you set it the wrong way, you can get unintended consequences, right? So if you set a game such that, like for instance, just existing, you get a 0.1 reward, it may lead to like a guy with no, or you know, like a player with no goals, and it'll just do nothing. So you have to be mindful as you're setting the rewards if it just doesn't make sense. Or sometimes if you set the world to be so negative, you'll see like basically the robot go and commit suicide, basically. Like it'll just go and fall off a cliff because it's better than staying alive and like getting more bad rewards, you know? So you want to avoid those. But the good examples is right here, like it's that animation over there. Basically, the distance from your boss is basically how much free speech you have, you know? So you kind of see, it's like, oh man, the agent's like really near, that boss is gonna try to run away. And right now it's like, oh crap, and I'll go nowhere. There you go, it's kind of like that, okay? And negative rewards is useful though, because especially when you're trying to maximize or minimize time. For instance, you have a maze, right? You have a maze and each step incurs a -1 reward. It's very, very well defined because if you finish the maze in the least amount of steps, you are penalized less. Does that make sense? So it's a great way to like basically implement an exit strategy over time. Does that make sense? Kind of, right? Okay. So why is DQM being adopted? The main reason is because it's model-less and it's very general purpose. And it can be run with no human intervention because, like we told you before, the supervised part of it is automated by, some function. And the learning happens online, meaning that you can just throw it into the world and then it'll just start prescribing actions. And the algorithm, as you're going to see, is really easy to reason about. We just have a brain that takes cues from the environment. From these cues, we will suggest an action, and then these actions may incur positive or negative rewards, and based on these net rewards and estimations, we'll update the learnings to maximize positive outcomes, okay? And experience replay, I put this here just so that you're aware, as if you're starting to research it, you'll like it. It's a powerful trick, and basically what it means is it just keeps track of, let's say, 10,000 of the last plays, like 10,000 of the last 8 action pairs, right, that it did, and the rewards. And it can sample from that memory to replay in the environment to see if it gets different outcomes. So you don't need a gigantic testing environment. You can learn from your past experience as well. And the other cool thing is it generally works. When it doesn't work, right? So it doesn't work when you can't model accurately the Earth environment. For instance, if I wanted to model heaven and hell, I would have no clue, And it also doesn't work if if the success requires long and exact sequential actions. So just look at this chart. This is basically just like Pac-Man, except it needs to get here. Ooh, what's that? Delete. Oh, sorry. Exit. Okay. Sorry about that. That's so weird. Okay. I wonder how I can change this. Oh, there we go. Okay. So for this maze, for instance, if it has up, down, left, right actions and no rewards all around it, how is it ever going to find that little tiny hole in which it has to enter before going right, up, right, down, right to get the check mark? And even when it gets it, what the heck would it have learned? So you have to be mindful of that as well, okay? And it also doesn't work if the rewards are too sparse, meaning that I go, 1,000 right turns, and then I get one reward of +1, and then I go 1,000 more and nothing, It doesn't reinforce anything. So you have to be mindful of that as well. And it also doesn't work when the environment can't be adequately observed. Maybe our sensor technology, we don't have anything to measure what we need to measure. So it's just those kinds of things. Reward structure might not be obvious, or we can't afford to make mistakes. Like for instance, if you put this in a self-driving car and it's up on a cliff and it's a left turn to fall off, you don't want that to be the random action, to happen. So you can't afford it. Or you just might not have time. And yeah, what does not working mean? It just means that training does not improve performance above random. All right, cool. Finally, we're going to get into some code. So the framework looks kind of like this. So all the brain and pretty much everything is encompassed in these 7 files, basically. A bunch of them are components, and the 3 main ones that we need to look at is agent.cfc, index.cfm, and utils.cfc. So your state and your actions get defined in agent, and your front-end logic goes into index.cfm, utils.cfc has 2 helper functions that you will use. One is reset everything, which basically just kind of nukes the brain, nukes the agent, nukes the everything so you can start fresh. And then the other one is force reward, meaning that after you prescribed an action, right, I might want to call an AJAX call to the server and tell it, oh man, that action that you gave me was a good one after the fact. So that's why that's there, and that's why they're remote. So you'll see we'll use that quite a lot. And agent.cfc has a couple methods or a couple aspects in it that's noteworthy. The first one is how do you define your actions? So it's right here. It's just this actions is an array of stuff. And right now I'm going to prescribe one of these colors that I think you like. Okay? Green, yellow, blue, violet, whatever. And the brain right here, you'll notice that agent.cfc nulls the brain, so the brain's set externally. So we'll see it in index.cfm when we actually set everything up. Digestion signal is super important. I don't know why I didn't call that rewards, but that's what it is. Digestion signal is just how much reward are we capturing, or how much reward are we like ticking up at this point in time. Okay? And this action outputs to the world, this is just an initial variable. So right now it's just set to 0, so it's nothing. Num states is important, it's just really how many dimensions is in the inputs. So how many dimensions is in the states variable. So for the Pac-Man example, we have 30 sensors times 3 objects, roughly, I don't know, like 150 states or so. So it gives you a rough idea of what you can do. Next up is the forward function, and this is the function that advances the agent, meaning this is the prescriber. So anytime that you want to ask the Adobe brain to give me an action, you go agent.brain.forward, and then it would just prescribe you an action, basically. But we'll see that more later, it'll make more sense. But you'll see here, the forward function has like an input array. So whatever you think represents the state space should be parameterized or arrayified right there. And that determines the number of dimensions in play. And that sets the neural network appropriately sized. Okay? And you see here, this is the action suggester or the prescriber. It just calls this.brain.act on the input array. Okay? And out comes what was above, one of these set of actions. Okay? I hope you guys are following. But okay, other helpful stuff. The only one important here is really backward function. So backward function, you call that whenever you want it to backpropagate and learn from the last X number of actions. Okay? So you would go forward, 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 or even forward and backward, forward and backward. Backwards is just backpropagation. Okay? And for index.cfm, you'll see this is the general setup, and you can just use this if you want. But gamma is the discount factor, so the farther into the future, it'll just be discounted by 10%, 10%, 10% until it's nil. And the second important thing is actually epsilon. So epsilon is your randomization quotient. So if you think about it this way, it's like, okay, I go and I learn a policy, right? And I learned that if I, again, turn right on Elm Street, it always led me to positive rewards. But every now and again, this epsilon is set at 20% of the time. It will take a random action, just in case there's something new to be considered, and so that you can dig yourself out of a hole, right? So it's prescribing me black as my favorite color, like 4 out of 5 times. But on that 5th time, it'll prescribe me pink, just in case my taste might change in the future. So I have an escape outside of the policy. Okay? Other stuff would be, here we're setting it in the server scope because I wanted it to persist. But you guys can choose, I don't know, session scope, it's up to you. But this is how you initialize the library. And then this is how you set up an agent. And then finally, the environment variable is right now set to just the agent, but you can add more stuff to that. That's the only reason I made it as a separate variable. And then from those, you're going to initialize the brain. So server.agent.brain is going to set itself to call the DQ agent function, okay? Passing in the environment and the spec, which is this guy right here. So that's all you need to basically get a pretty primitive brain going in CF, okay? And right here, you see on the bottom, I really should not put stuff down there. You can see right here that I'm resetting the reward base back to 0, and then I'm calling a forward function immediately, meaning prescribing an action, prescribing me a UI, okay? And that's pretty much it. These other useful stuff we can talk about, but the one that I'll point out is basically this guy right here. The write output utils.cfc method, force reward, and reset everything. So it was what I was telling you guys about before, like your Ajax calls, calling after the fact. We're gonna use that to death, basically. Okay, other cool things is if you ever wanted to, after learning everything, if you ever wanted to export the brain, then you would just call whatever you set your agent was, .brain.toJSON, and out comes the JSON object. So you can pass on to other people, or you can load it later. Does that make sense? Kind of? Okay. Time for demos. Excellent. All right, so basic example, we'll do this one. So I'm gonna basically prescribe myself a color, okay, out of those 7 that we were talking about, and I'm just going to say if I like it or not. And eventually it should converge to the color that I like. That's a really simple example, right? So the state space is 1, I'm just a generic user. The action space is 5, or whatever. Sorry about that. That's actually the number of colors. And the colors here, 80% of the time it will use what it learned, and 20% of the time it'll be epsilon, will be random, so that I can get myself out. And if I click on like, it'll be +1. Now no like would be -1. Okay? So what does that look like? It will be like this. So if I keep refreshing, it's a bunch of random and sometimes not random colors. And the last rewards is nothing. Ooh, interesting. Okay, I'll just say I don't like. Accept everything. Oh no! Alright, I don't like it. There we go. Like, oh, I don't like it. Yes, I like purple, but not anymore. Oh, I like yellow too. You know? And basically what you're seeing over here is a list of last rewards. But I can say that I like yellow a lot and always like yellow only, and no like here. Yes, I really like it. But basically you're going to see it converge to always be yellow until I start not liking it a lot, right? Which makes sense. If I don't like yellow a lot, eventually it'll unlearn all that and prescribe me another thing. Does that make sense? And if I keep clicking no like, it'll just give me a different color after a couple tries. So that's essentially what's happening, and you might think it's like, oh man, this is such a simple example. I could just create a table and track all these things, right? But then what if your input space becomes 1,000 and you can't reason about it anymore? That's when this comes in. Does that make sense? So it's a super easy example here, but yeah, it's functional. The next example is just the color generalizing. So I'm going to show you that. Let's see. Make dark. And I'll show you the code for that too. And if I go reset everything and refresh, here we go. So now the assumption is I am a dude and I like dark colors. So here, it's just the UI, okay, of 4 things. And what does that look like? Let me see if I can. Go here. Open index.cfm. Code looks like so. And over here, these are the 2 only files that you need to work with as you're like creating these demos. So the action space here is discrete, right? There's only really 5, 6 options. And these are the ones that will be displayed. And it'll just be random from like these 1, 2, 3, 4, 5 options. But the crazy thing is I put in the rewards. Let's see. Right down here is the rest of the UI. But I put in the rewards, like I right now am a map. So if it contains dark colors, I'm just gonna specifically make the clicks positive for me, and the rest will be negative. So as you're seeing this, it's prescribing the whole entire UI in one shot. So it's giving me the 4 colors. But what I'm going to do is I'm going to basically pick the least favorite colors of mine, and then I'll refresh. And it gave me a bunch of darks, and I'm like, okay, I guess that's the less bright one. It'll keep going. Ooh, wow, that's very good because just luck. But yeah, so what we're looking for here is just a policy in which it will give me more dark colors because that's my preference, or that's my presumed preference. So as you click this, it will just keep going. Okay? Let's see. That still has some messed up. It's still going, but each time you're clicking, let me see if I can show you. I hope it's working. Network. Each time it's clicking, you can kind of see it shooting CF, basically a negative reward for this one. And I'm basically just resetting. And hopefully it goes up this loop. There we go. But after hundreds of iterations, it will converge to basically the all dark palette. Okay? But that's this guy right here. The last example is probably going to be the most applicable one. So it's very similar to the color profiling one that I just showed you, but now it's a dynamic UI. So what do I mean by that? Let me pull up this and show you and bring back the slide in a second. So here, check out, branch, and then go back here, reset everything because I want to nuke the brain and everything, refresh. There we go. Okay. So let's clear out this guy and see what the heck is going on here. So go to console, make sure I'm at 100% view. Am I? I am at 100. Okay, cool. So this one is more likely useful to everyone here. But what's happening here is, okay, you have 9 variations of a header banner. You have maybe 3 of like this middle one. And then you might have a couple more of these, right? And the goal of this problem is, okay, so one frame that you prescribe to a user would be just one of the many combinations that can be formed, right? And the thinking here is each one of those frames should become a discrete action that the brain will prescribe. Okay, so we'll do that by basically just applying the Cartesian products on arrays to get all the combinations. But I'll show you in a second. And the state space here is 2. I can either be male or female with some generalizations. So the action space here is actually a couple hundred. It's getting a little bit bigger. It's possible to get A1, B1, C1, or it's possible to get A1, B1, C2, all these things. But that doesn't matter because we're just going to track it as, if they like it, it'll be a +1 reward for this whole entire panel. Okay, the whole entire UI gets a +1 for it. And then we're also looking at ticks, meaning that, okay, if you're looking at something, it'll also incur like a reward. So that's what's happening here. So right now I'm a female, and I'm looking at this based off of like some logic. For instance, men might prefer confident, very, very, very powerful text, or less about family, I don't know. Or females might prefer more sensitive language, or more planning, or whatever it may be. But that can go into your reward structure. But right here, you can kind of see, based on my assumptions anyway, if you're looking at, right now, A9 and B4, right? And that compares to a -2 plus a +3, that becomes net 1. So then it shoots to the server what the total tally of that was. So I'm just tracking this, and if I refresh it, it will be a slightly better or random version, and it'll incur the reward of 188 for that last panel. And over time, over many users, it should converge to basically a UI that it thinks is perfect for you based on whatever inputs that you have. So yeah, that's that example. But where do we go from here? There's a lot to do, to be honest. I only implemented like one algorithm in CF, and if it catches on, I'll keep adding more. But for me, it was just an exploration exercise. So maybe we can implement a couple other ones, like tooling, DQN, or add a different neural net implementation, or maybe like multiple agents. So right now it doesn't work. It's pretty much serial, meaning that the threading is just one. I haven't really figured that out yet. But also, I've been thinking also, how do I say this? Okay, basically the server side being the brain and managing all the Ajax requests and stuff, there comes a point where the latency really does get to you. So what I'm thinking is probably adding like a separate like JavaScript side so that you can do some thinking and some reasoning on the JavaScript side and then shoot its learnings back to like, ColdFusion to like store and like save the key. So because of that, that's why you have the to JSON and from JSON so that you can load brains back and forth. But there's a lot left to do. That's basically it, but let me see. Like multiple agents, why is that important? let's see, 1, 7, index. Hopefully, I'm going to try to pull a multiple agent one. Master. Oh no, not master. Regeneration. There we go. I think this will work. And we've got this. Wow, that's really fast. Ooh. Okay. Let's go here. There we go. So multiple agents would look something like this. So instead of just one Batman, like now let's say we made 5, and each one is with its own separate brain. And you can kind of see that there's only one smart one there, the rest of it has been reset. So yeah, I don't know if you can pick them up, there's probably that middle one that's doing really well. But yep. So the resources and stuff, you can find it basically on draftstudios.com, right at the top. The presentation slides and the rigging demo and even that Pac-Man example and all that stuff is in there. More resources, it's quite a lot to study. So I added basically 2 panels of stuff. If you just wanted to read and just peruse and play, that's really all I can hope for. But reading it's actually pretty intriguing. So definitely worth the time. So these are the resources I would suggest, and just read it. And if you want to contribute or just poke fun at it, just do whatever. Feel free to download. But yeah, that's pretty much all I got for you. But it's just an exploration type of talk this time. And I wish I could have gone in more detail, but that's all I got. Do you guys have any questions? Or oh, the link of the presentation? Sorry. It would be basically right here. So if you go to there, right at the top, this guy right here. Hopefully that works, but here, I will pull this back. There we go. Sorry about that. And it's a lot to digest, but yeah.
So the brain came from where?
Oh, yeah, the brain is a generic, basically the DQN, the DQ learning is an algorithm that was made by, I believe, DeepMind. So it came from a paper from like 2013 or 2015, around there. So I basically just rewrote it again in CF. So if you want to see what that looks like, it's right here. So it would be under the lib. Let me bump these guys up. Okay, LS. And it would be here. 3 CF 4. So most of the code is in all these files right here. So all of these are important, but some more than others. This guy is really important.
The brain there?
The brain is, yeah, let's see. Yep, the brain is basically DQN agent right here. So it's this guy. This one is the brain.
And then it calls like brain.learn at the bottom, which calls it.
Yeah, here. Basically, you see a DQN agent right here. It actually instantiates the reinforce library. And then from there, it has a bunch of other stuff too, like reset here. It's just a bunch of matrix math, 2JSON. Let me see. The place where you would set the brain is actually up a directory in index.cfm. Sorry, moving around a bit. Right here. Right here. This guy right here. That's how you do it. So server, you set up the agent first, which is this one right here. They're instantiating an agent, but it doesn't have a brain yet. So you actually add it into the agent, right? Using server.obj.dq agent. So here you will see the call. Obj is reinforce RL, which is quite a lot of stuff too, right here. And then look for DQN. There we go. So all that's doing is it's creating another DQN agent right here.
So you took that Stanford MIT module and you recoded it in ColdFusion?
Pretty much, yeah.
Wow.
The only sucky thing about it was the matrix math sucked because we were index of 1. And I'm just like, oh man. So it's just a lot of like, oh shoot, I messed up there, you know? But yeah, you'll see a lot of these things, but it's a lot to digest. But I do suggest just jumping in, opening up master branch, opening up this CFM right here. Let me close up a couple of these. It's getting quite big. Yeah, like just opening up one of these guys and just reading through it. Oh, there's a lot of stuff here, but gamma is important, epsilon, like I said, is important. But usually you see people as they're shipping out software, they set epsilon to 0, actually. After they finish their learning, like in their controlled environment, they'll set it to 0 before releasing a patch update to the software so that the brain doesn't do anything unexpected. So that kind of makes sense. Like you don't want it to be testing on you. So yeah.
So you said you can export the
yes.
the brain learning
sure.
to JSON file.
Yes, I will show you that right now. So let me see. Even this one would work, but let's just go.
So that can be reused.
Yes. The thinking is, then you can basically reload it or save states of it. It's like, oh man, that's a downturn, so reset it to something older. But let's see, so where am I now? I reset everything, I'm here. Okay, so you wanted to dump the brain? Let's go dump the brain. So index.cfm should have this. Up here, and right down here, let's just take this guy right here and paste it. I guess I'll just put that there. So I'm going to dump basically the brain and refresh, and hopefully it works. But the brain at its current state looks something like this. God help. Where is it? Oh man, where did it go? Okay, these things. Don't need an action. Reset. Kind of want to just nuke everything. So let's do it. And just dump this out. Let's try that again. Refresh. There we go. Okay. So basically you can take this guy, store it somewhere, and you can import it again, basically using something like this. So you would set server, brain, right? From JSON, this little grabber, and that should actually work. Yeah, so you refresh that, and that, will actually work. Does that kind of make sense?
Yeah. And store it for you.
Yeah, it's pretty funky. Any other questions? And sorry if I put you guys to sleep.
If you, like, in a particular case where you're like trying to test a call to action or something like that,
yes,
it seems like more clear, like, okay, you have, like, you do an A/B, like, split test sort of thing.
Yep.
But how would you recommend getting, like, if you're talking about, like, the layout of the page where there's like 10 different elements, how do you decide
I know what you're getting
this
at.
is important, this is not important?
Correct. The main reason, okay, so for that, the kind of downside, I guess it is a downside, is that it needs to be discrete, or at least it should be discrete. So what I've been doing is I've been treating the whole frame as like one action. So your combinations, let me see if I can pull it up here. Undo, I think it's under H. I'm kind of messing up my code a little bit. But right here, you can kind of see like all the images. So for the first panel, it's between A1 and A9, right? And then the second panel is between B1, B2. I don't know why C1s and stuff are all there as well, but it is. Oh, that's because my indentation was bad. Sorry, $3. Take this guy down. That looks a little better. Okay, but anyway, right there. But yeah, so these are all the combinations. So the only way I've been able to solve it is basically run the Cartesian product of it and treat that whole entire UI as level one. And then the hope here is just to generalize the entire, all the components shown on the screen at once. But the only other way to do it, how would I do it? If you wanted to do A/B testing, how would I do it? Yeah, I couldn't solve that. I basically had to just discretize it and treat like the whole UI, and then the rewards are based off that whole action. I guess the only way would be to create multiple different actions with different agents and different brains for each component piece is probably the only way out. So that this one is only responsible for A1, like the header band, and it has 9 possible options. It will optimize those 9 if you want it that way. But for me, I took the whole snapshot basically. I took this whole right here, like this frame as a whole, as one action pool. So then I have to grade it as a whole. So it would probably take longer to converge to something good. Does that kind of answer your question?
I think so.
But you would need probably a separate framework or a separate brain and agent for each one of your call to actions if you wanted to optimize just one. Makes sense, right? Yeah. Any other questions?
Is that a requirement for the actions to be discrete, to be limited to second?
Not exactly.
So you can probably like do a Cartesian of like.
Yeah, you can, and then it would be pretty nuts, but I can't reason about it, so it's like, oh man.
Right.
So for now, I just have to play this simple. Because like even the Pac-Man one, if you ran it at really fast for like, who was it? Oh, he did. Yeah, like he did for a little while. It was basically just burn out your laptop. Yeah, it's crazy. It's pretty crazy. But yeah, it just gets really intensive. But yeah. That's it, yeah.